Hello, Miss Walsh here. So today we're going to do something a little bit different. We are going to be covering a little topic called optimization. This is a really important topic. And what optimization means is it means the best possible solution. Okay, sometimes that means finding the most of something. Sometimes that means finding the best of something. Okay, it is a little bit time consuming, so this will probably take a little bit longer than the usual podcasts. Okay, so we've got a rectangular cake dish that is made by cutting out squares from the corners from a 25 by 40 centimeter tin plate and then folding the metal to form a container. We're keeping things a little bit simple here in a sense of what we're doing is we just cut it out and then we fold it up. So there isn't any overlap material, okay? So hopefully you can see that this side right here, or any side of these that is cut out, and then when it's folded up, it becomes this height right here, okay? Now, the way that you use this sheet of 25 by 40, the way that the size of the corners that you cut out matters, and it will change the volume. So you can think, well, maybe it's in your interest to cut a square a little bit bigger, because then when you fold it up, then your height will be higher. So you would lose a little bit of that square base, or it's not a square, you would lose a little bit of the base, but your container would be higher. Or perhaps it's in your interest to cut teeny tiny little squares like this, right? And just fold it up. And then this would be very, very, very short, but then your base rectangle would be quite large. So what we want to do is we want to find a way to generalize this and then get the maximum volume. So when you do these optimization problems, what you always will have is you will always have your optimization functions. What do you want to optimize, okay? So to optimize, and what we want to find here is we want to find the maximum volume, okay? So we're going to write volume here. And what we want is we want the volume of this rectangular box, and the volume formula for the rectangular box is going to be length times width on the bottom, and then times the height that we folded up. Okay, you've seen this formula before. Okay, now of course it would be nice to make a box as large as all can be, but we always have certain constraints. And this is general everywhere, right? That sure, you would like to produce more of something, but perhaps you're constrained by the material that you can afford, or you guys would like to, earn the best possible grades and to learn absolutely everything that's assigned. But sometimes, as you know, you're constrained by the time that you have. So what are our constraints? Well, our constraints are the fact that we have here a 24 by 40. Okay, so our constraints are going to be our base times our height. Okay, so whatever we are cutting out, this side is, we are going to call this x. Okay, so we're going to have our sides. We're going to have x. Our side, therefore, here will be, the length will be 25 minus 2x. And the reason that it's minus 2x is because you have this length of 25, but you're cutting it from here and from here. So it's 25 minus 2x. And we also have 40 minus 2x. Now, just a little formal note, you won't have to worry about it, but the x will be greater or equal to 0, and we know that it can't be longer than this side. Okay, so you're gonna have 25 minus 2x. You're gonna need some sort of a length, so that's going to be greater than 0. And then if we solve for the x, then x is gonna have to be less than 12.5. That's just where your answer will lie. You don't have to worry about this, and you don't even have to do it on the test. We're just interested in setting up this function, okay? So here we go. And what we can do now is we can set up our volume function, and we can do it just in terms of x. Okay, so our function then is going to be, volume is going to be x times 25 minus 2x and 40 minus 2x. So now, depending on the size of x that you choose, you can get all sorts of different volumes. And there are interesting ways to find what the max is. This is actually our function. What we are going to do is we're just going to graph it on the GDC, okay? So let's go to the GDC. And again, you might want to pause just to make sure that you do it, because what I've done is I've actually entered it so that just for the sake of how long this is. Okay, so I'm gonna hit plot, and your plot may not look like this, but basically try to play around with the numbers. You can also try, if you go to the view, then you can also try auto scale. Okay, so try that. And once you have the plot, 1 second, it'll come back. So if we go to view and just auto scale, you see that what this is these are the different x's, and the y is the volume. And I'm just going to go to the table of values. These are all the possible volumes that we can get. So I don't want to, let me just start with 1. So look, if I use an x of 1, then my volume would be 874. And somewhere here is the biggest possible result. It's not necessarily an integer, right? So you have to be careful about just reading the biggest number here. So let's see what it is, okay? So we can see that the answer will lie somewhere there. And so if we just go to the function and the extremum, we can see that the maximum occurs at 5, 25, 50. So and so therefore, it's asking us what size squares must be cut out. So the x that we cut out must be 5, or that you can say that the size of the square must be a 5 by 5. Alternately, if you're asked what is the maximum volume, then you would say that the maximum volume that you would get for this problem is 2250 cubic centimeters. So it's kind of interesting because you do, as you can see, depending on what you cut out and then fold up, you do get very different volumes indeed, even though you're using the same sheet of tin. All right, second problem coming right up. Bye.